A lithium battery is certified as an installed fire source, not as a power supply. That right there is the foundational engineering axiom of modern aircraft battery certification. It's a massive paradigm shift, and it establishes the absolute baseline reality that we, as aerospace engineers, have to design around. Section 1, the regulatory chemistry gap. So why does this axiom even exist? Well, we have to look at a fundamental mismatch. The baseline aircraft battery rules in Part 25 were recodified way back in 1965. They were written entirely around nickel-cadmium and lead-acid designs. Those are legacy chemistries with slow, highly predictable failure modes. But lithium chemistry, with its immense energy density and chemical volatility, it just wasn't envisioned by those 1965 rules. Because the existing baseline simply doesn't cover it, the FAA has to issue special conditions for lithium battery installations, adding rigorous safety requirements that go far beyond those legacy regulations. Section 2, defining runaway and propagation. The hazard driving every single one of these special conditions is rooted entirely in thermodynamic physics. First, we need to define thermal runaway as a distinct condition. It's a rapid, self-sustaining exothermic chain reaction. It causes a violent rise in cell temperature and pressure, venting flammable and toxic gas. But here's why it's an independent hazard. The decomposing cell actually generates its own oxygen. That means combustion proceeds entirely independently of external air. Now, we have to explicitly differentiate that from thermal runaway propagation. Propagation is the spread of that initial thermal runaway, cascading from a single failing cell to adjacent cells within the battery pack. Propagation isn't just a failure. It is the catastrophic cell-to-cell spread of that failure. Section 3. Propagation drives regulatory requirements. This highly specific propagation behavior is what completely dictates our current regulatory framework. You see, FAA Technical Center fire testing proved a critical point. When a cell enters thermal runaway, traditional Halon 1301 fire suppression will successfully extinguish the resulting electrolyte fire. However, it entirely fails to stop the runaway from spreading from cell to cell. Why? Because the internal heat generation simply outpaces any heat dissipation, creating an unstoppable positive feedback loop. Because this propagation cannot be stopped by traditional suppression, the regulatory standard doesn't try to prove a cell will never fail. Honestly, that's impossible. Instead, certification assumes that one cell will fail, and it strictly mandates that the engineering design must completely contain it. Section 4. Qualification versus installation approval. To manage this strict contained failure requirement, aerospace engineers utilize a two-step certification matrix. And it's vital to understand these are distinct steps. Qualification approval certifies that the standalone battery component meets minimum performance and safety standards on a bench. Installation approval, on the other hand, certifies the physical integration, thermal management, and venting of that battery within a specific airframe. Simply qualifying a battery component does not legally authorize its installation on an aircraft. This matrix brilliantly illustrates how the process functions. On the qualification side, standards like DO-311A dictate rigorous overcharge and thermal runaway containment testing, while DO-160G and DO-178C handle environmental factors and software. But remember, installation approval is an entirely separate layer that utilizes Advisory Circular 20-184 to ensure proper airframe integration. Each standard across this matrix addresses a highly specific layer of the battery's thermodynamics and systems architecture. Certifying a lithium battery is not about proving it works. It is about proving what happens when it fails.